Hello, lovelies. This is our first video lecture, which is kind of surprising because usually we're way far behind and we have to do more, but this is a great one. We are going to talk about osmosis, which is in your notes under osmosis, right after freezing point and boiling point. Osmosis occurs when a solution is separated from a pure solvent by a semi-permeable membrane. Your capillaries are semi-permeable membranes. That's why we talk about it. Your cells are semi-permeable membranes, which means some things can go in and some things can go out. Think of it, I'm a girl, so the boys are going to have to help me. I think of it like pantyhose is kind of a semi-permeable membrane. You could put things in there, water can come in and out, but the big things can't come in and out of the pantyhose. We're going to play with this in lab or have some dialysis tubing, also have some things for you to play with. But this is what osmosis is. It occurs when a solution is separated from a pure solvent by a semi-permeable membrane. So what this picture is showing you is if you have this long tube and under here, think of it as pantyhose. All right, just for the purpose of this class, it's pantyhose under here, the semi-permeable membrane. And there's water in here. Well, water is going to go, everything's going to go, just like gas, from a high concentration to a low concentration. Think about diffusion, something stinky. It goes, if I open a bottle of something smelly, it's going to go from a high concentration of stinky, and all of you are going to share in the stinky, right? Everything goes from a high concentration to a low concentration. So in here is a high concentration. Well, if that can't get out, then water is going to go in here and say, oh my gosh, we got to get it out. Everything has to be at equilibrium. Water's like that. It's like, I just want everyone to be equal. Please, let's all just be equal. So water's like, we got to make it equal. We got to do something. I got to dilute it. So water rushes in here to try and dilute this. You will see this over time. So what this is depicting is I put my pantyhose in here. I put a bunch of, I don't know, gummy bears, something. I put some high concentration of syrup or sugar or something in here and it can't get out from the semi-permeable membrane. Over time, the water is going to rush in here and say, I just have to dilute it. So do you see where the water is here? Do you see where the water is here? Except it rushed in here and you can see it up here. This is called osmotic pressure. So let's define osmosis again. Osmosis occurs when a solvent, when a solution is separated, wait a minute, occurs when a solution is separated. We already did that one. So osmosis, again, is the passage of a solvent through a semi-permeable membrane separated by two concentrations. Osmotic pressure, that's the next thing on your list. Osmotic pressure depends on the amount of external pressure that must be applied to a solution to prevent the net movement of a solvent. So this is the osmotic pressure. If I pushed on this little thing right here, if I pushed with my little tiny finger and shoved that water back down in there, it would go back out. So this is osmotic pressure, the amount of external pressure, shoving a little finger down there, that must be applied to a solution to prevent the movement of solvents across a semi-permeable membrane. So sometimes your body does this, but it's just measured. It's measured how much do you need to put the blood here or to move it there. So we're going to see this osmotic pressure. This is going to come up a lot in physiology. Okay. If you didn't get that, you have to pause it, sorry. As the liquid in the tube rises, its weight creates a pressure that pushes the solvent back through the membrane until the rates forward and backward are equal. So you don't get this osmotic pressure after a time. It'll be an hour or so, and then you can say, okay, it's not going up and down anymore. It's stable, and that's when you can measure your osmotic pressure. And, of course, there is an equation for this, because there's an equation for everything, and you should have this equation written down here. Osmotic pressure depends only on the concentration of solute particles. We're assuming everything is in water, really. So really all we care about is this solute concentration and how much stuff is in there. How goopy is it? Is it syrup? Is it just sugar water? Is it pure syrup? What is in there? And that's going to be your osmotic pressure. That's the equation. When a solvent and a solution contain particles and they are separated by a semi-permeable membrane, the solution is said to have a higher osmotic pressure. So remember, the syrup in my pantyhose, the syrup is going to have the higher osmotic pressure than the pure solvent. So the pure solvent or the water is going to rush in to try and dilute the syrup. And that's what's going to have the high osmotic pressure. So high osmotic pressure is concentration. It's kind of another way to say concentration. But we just say it when it's in terms of semi-permeable membranes. N. It is the thing that we are measuring, the syrup or the sugar or the proteins or whatever it is. It's not counting the pure solvent. How do we count osmolarity? We use the equation. Osmolarity is the sum of the molarities of all the dissolved particles in a solution. So again, this is kind of like combined gas law. Osmolarity is like, I don't care what you are. I don't care if you're a sugar molecule. I don't care if you're nitrogen. I don't care if you're chlorine. I don't care what you are. I'm going to count everybody all together. How concentrated is this? What kind of goop are we talking about on the other end of this semi-permeable membrane? And that's going to be your osmolarity. It's going to be measured in osmoles. And you will see this come up in physiology as we move things around in your body, as things go from here, point A to point B. You're going to see this osmole calculation come up again and again. That is osmolarity. Why do I care about this? Because you will kill me. I'm not even joking. This is how people kill people, because they don't get it. They don't get that your capillaries are not a bunch of blood cells floating around in water. That would be weird. It's not water in there. It's blood. Think of it as a saline solution. So osmosis is particularly important in living things, and we want to keep them alive, so that's why we want to remember this. Because the membranes around the cells are semi-permeable. So, if you're not trying to kill me, you have an isotonic solution. An isotonic solution is awesome because that means that whatever the concentration of in your blood, see this happy little blood cell right here? It means nothing's coming in, nothing's going out, everybody's happy. This is a nice IV drip full of saline solution that is exactly the same concentration as your capillaries. See how nice that is? Here is, I am totally a moron, and I'm going to kill you. So here's what happens. Isotonic, a hypotonic solution having an osmolarity less than the surrounding blood cells. That's bad. So hypotonic is your osmolarity is less. Let's look at the next one. Hyper. You're going to confuse these. Hypo, hyper. Having an osmolarity greater than the surrounding blood cell. This is when you try and make your own. So here's a bunch of water rushing in to try and it busts up that blood cell. That's bad. You don't want that. None of these things are good. You don't want any of these things. Let's talk about what you need. You need a 0.9% physiological saline solution. This is what your IV drip is. You're going to put an IV drip in me, and I'm going to be happy as a little clam because I'm not going to die. Because my capillaries are not going to know anything's going on. They're going to know there's some more liquid, but it's not weird liquid. My blood cells are going to look like that. See, that's a happy blood cell right there because somebody used an isotonic solution, which is 9% saline or 0.15 molar NaCl. Right? Everybody's happy. Here's some sad blood cells right here. Distilled water. This is how morons kill people. They say, oh, you're dehydrated? I don't have any IV fluid. I should just put a IV needle in you and run straight distilled water through your veins into your capillaries. Here's what happens. Blood cells placed in water hemolyze. They swell up. Because what's the water going to want to do? Right? The water's like, oh my gosh, look at all this blood cell stuff. I got to get in there and dilute that. Right? That's what water does. It's like, man, I got to get in there and dilute it. Let me dilute it. I've got to dilute it. Water wants to dilute things. That's what it does. That's who it is. So water's going to go in there, and this is when it all gets real bad. This is like, okay, you're just an idiot and we can fix it. This is like, no, now you've lysed the cells and they've exploded. You can imagine that's not good when your blood cells start exploding. This is how you kill me. This is why I teach this class, to make sure that you don't kill me. So this is another, maybe I'll put some sugar in there. I don't know how people do this, but this is like you double the concentration of the physiological saline solution. You don't know how to do molars. I don't know, something happens and you don't get the saline solution right and you run an IV drip through somebody who has a super concentrated solution. So you have syrup blood. You just ran syrup through someone's IV. You're like, oh, they're depressed. You know what they need? Sugar. So I'm just going to slap some sugar in their IV. Don't do that. Their blood cells will look like this. Because what does water want to do? Water wants to dilute things. So water's like, man, I got to get out of here and dilute this syrup blood. So the water leaves the blood cell. It's supposed to look like this, and it looks like that. All